Good morning, everyone. Let's. Good morning, sir. Good morning. So let's start.
Yes, sir.
Yesterday, yeah. Any questions from yesterday? Assuming none. So we discussed video properties. We discussed audio properties. And we understood the bandwidth requirement depends upon encoding, whether audio encoding, PCM encoding, or otherwise. Video we look at spatial, temporal. Then we looked at requirements for stored multimedia streaming. Now let's look at what are the different technologies that could happen. We look at three technologies. One is called UDP streaming, next is HTTP streaming, and third is a DAS, that is dynamic adaptive streaming over HTTP. Basically HTTP, but dynamically adjusted. So we look at all three and understand what it involves, and then you get into more application level multicasting such as CDN that will go in the next lecture. We all know UDP, we studied that. So first protocol was done implementing UDP. Typically what happens is when you want to play a multimedia video using UDP, server knows what is the encoding rate of the media application of multimedia, whether video was encoded at the rate of 2 Mbps or 3 Mbps or whatever rate, because whatever rate video was encoded, it has to be played at the same rate at the client. And that means server knows is their client rate. So server using UDP will send the data at the same rate, which is encoding rate, which is same as playing rate. Now, so UDP will keep pumping data at this rate. Does not matter what the network bandwidth is. We have studied UDP, there is no congestion control. If network has a capacity, packet will be transmitted. If network doesn't have a capacity, packet would be lost. There is no retransmission of packets in UDP. So, if network is congested, server sending more packets will cause more congestion, more packets will be dropped. If network is free, packets will go through. And that's the real challenge. So let's understand by an example, what do you mean by UDP transmission rate? Consider that a video was recorded at the rate of 2 megabits per second. That means a client should play the video at the rate of 2 megabits per second. Consider that each UDP packet is of size 1 kilobyte. The client has to play the video at the rate of 2 megabits per second. Each UDP packet the server is sending, each UDP packet size is 1 kilobyte. So at what rate packet should be sent? Can somebody like to calculate? So at what frequency we are having this is the rate, so client should get data at the rate of 2 megabits per second. Data comes in chunks of 1 kilobyte per packet. So in 1 second, how many packets client would receive and at what rate, that is what frequency should each packet be sent every 1 millisecond, 10 millisecond, 5 millisecond. So what rate, because server need to send the packets at the constant rate. The UDP packet, which is 1 kilobyte, at what rate server should be sending packet? That means per pack, every packet should go every 1 millisecond, 2 millisecond, 10 millisecond, whatever. Would someone like to calculate an answer? Given this requirement, at what frequency, at what rate, after how many milliseconds, each packet should be transmitted. Likhita S. Pavan P. Souvik Mandal. Saurabh Santosh. Are you there, Saurabh?
Yes, sir.
So tell me, how many packets per second client should receive or server should send? Our play rate or sending rate is 2 megabits per second, and each packet is 1 kilobyte. So how many packets server should send per second?
Sir, 2.
How? If I send 2 packets per second, what my rate would be? 16 kilobits per second. Because one packet is 8,000 bits. So 2 packets would give me 16,000 bits. But I need to play at the rate of 2 megabits. So how many packets server should send so that it can meet the play rate per second? Is the question too difficult? Shaktivel,
Yes, sir.
yeah. How many packets per second server should send? When my packet size is 1 kilobyte and my play rate is 2 megabits per second.
Sir, I should say the time, sir.
Question is, how many packets per second server should send?
Sir, 2.5, sir.
Okay, 2.5, how many data will constitute? One packet is 8,000 bits. So 2.5 packet, how much it will become?
20,000.
What is our requirement?
2 Mbps.
Our requirement is 2 megabits. Are you meeting that? Now can you tell me how many packets per second server need to send? And 2.5 is not the right answer.
Sir, 250.
250, yes. With 250 packet per second, we'll be able to meet our bandwidth. With 250 packet per second, what is the rate at which server should send? 250 per packet per second, meaning each packet should be transmitted at the interval of 4 milliseconds. So that is the rate server should keep transmitting the packet to the receiver. Now, if network is congested in between, this packet would be lost and there is no retransmission. And that is the one major drawback of UDP. But let's assume further and look at what are the other requirements of UDP. Now, you certainly would like to do some buffering initially, whether some transmission delay. So make initial transmission delay about 2 to 5 seconds because some variation may happen. So even though server is sending packets at 4 milliseconds, some packet may arrive early, some packet may arrive late. you want to keep a buffer for a certain time. So typically build a buffer of minimum 2 seconds, max 5, because more delay that user gets frustrated. You don't want to wait too long. Now, how does when some packets come out of order, because UDP is known to deliver packet out of order, or packet come out of too late, but time is running, they have to discard. So all this stuff, properly ordering a packet or playing in proper order, and if something comes out of order, discard it. So dealing at the application level, a protocol called RTP, real-time protocol, which runs on top of UDP. It basically shows that packets are played in the receiver. The packets are lost, they are lost. But whenever they receive buffering and playing, so the protocol RTP does this work. It basically deals with multimedia. However, the protocol is transparent to user actions. If user does a pause, what does server do? Let's say you are running a client server application UDP and client stop reading the data. Does server stop sending it? Server just keeps sending the data, whatever it has got. Server never stops sending it. So even the user has paused, the RTP protocol has no control mechanism to indicate to server that please stop sending because user has given a path. Or user is gonna fast forward, server has to send packet from that place. So there is no user control supported by RTP protocol, and thus a new protocol was defined called RTSP, real-time streaming protocol. The primary job of real-time streaming protocol is to support user actions. Pass, delete, so if I do a pass, it can tell server to stop sending, server could stop. If it is a fast forward, it can tell server start sending from that place, and so on and so forth. So UDP streaming involves two protocols, RTP, real-time protocol to transmit actual multimedia packet and playing it out. And second protocol, RTSP, or real-time streaming protocol to deal with user commands. So basically now we have two channels. One is the data channel, which is RTP. One is the control channel, which is RTSP. And it is very similar to our FTP. If we to recall back our discussion on FTP, we set up a control channel say get a file, and then data get transferred on a different channel. And that is what the FTP is. So data channel, control channel, same way RTSP works as a control channel and RTP works as data channel. If any error occurs, something goes wrong, it's the application that has to deal with. So what are the major drawbacks of UDP based streaming? Primarily, we look at if my network bandwidth is varying, server is not aware of it, server just keeps sending at the fixed rate. And if network bandwidth will become low, packets will be delayed too much, or they may be lost. If packets are delayed too much, receiver is going to discard them because they receive out of order and it cannot even play them. And so that means we deal with trouble. So what is expected is that network bandwidth should at least be more than the play rate. Because if it is less than the play rate, certainly would have problem. So consider a case where video consumption rate is 2 megabits per second. Network gives me a bandwidth of more than 2 megabits per second. Let's say network gives me a bandwidth of 2.5 megabits per second. So on the average, let's say my movie is 1 hour long, and for almost all 1 hour, network gives me bandwidth of 2.5 megabits per second. But let's say every minute, for about 5 seconds, bandwidth falls to 1 megabit per second. So on the average, network gives me bandwidth of 2.5 megabits per second. I would not have a problem. But let's say every minute, a bandwidth falls to 1 megabit per second. So every minute I will get the server is sending packet at the rate of 2 Mbps. Network is delivering at the rate of 1 megabit. I'll be losing some packets, so whatever in the buffer could play out, but anything beyond the buffer would not play out. And then user would basically have poor experience. All the client application has to do is video freeze. It's waiting for the data to come. Till data comes, it becomes a freeze, and that is the impact. And there is no control there. Because we are using a UDP, there is no congestion control built in. Server keeps sending it, there is no adjustment. Other major drawback is we need a separate server. We need a one RTP server to play. We need another server, RTSP server. That means from infrastructure perspective, we need to manage two kind of servers. And any deployment, more the moving parts, more the management issues. Thirdly, most of the network traffic in a corporate or house or somewhere always goes via firewall. And firewall in general allow HTTP traffic. Firewalls do not allow UDP traffic in general. And so they'll block a UDP traffic. To permit it, you need to make a hole. And that means no IT admin would like to make a hole in firewall, so that doesn't work. So major three drawbacks. One is that server has no control over the bandwidth they keep sending, and it may lead to user freeze when bandwidth falls. Second main drawback is we need a separate control server to deal with RTSP, to deal with user actions. And third is firewall issue, because most of the firewall only permit HTTP traffic, nothing else. And that means getting UDP traffic through the firewall would really be a challenge. So what best we can do next is go to TCP based streaming, which is HTTP protocol. When we work with HTTP works like you provide a URL and web server will send the file corresponding to URL. That means my video movie or video clip will be stored as a file on the server. Client does is give a URL and it gets the file, and once you get the file, it starts playing out. So HTTP works or runs on top of TCP. TCP congestion control is designed with the phenomena that it should probe the bandwidth of the network and should transmit data so that it can use the maximum optimally the bandwidth. If network bandwidth becomes 3 Mbps, it would try to send data at 3 Mbps. If network bandwidth becomes 1 Mbps, it tries to send data to 1 Mbps. That basically means, irrespective of what is the client play rate is, the server, the TCP connection will send the data based on what is the maximum bandwidth available. Because that is how TCP congestion control algorithm has been designed. So it will keep sending data as per the network bandwidth, adjusted. Data comes into the client application buffer, it gets stored and play out when certain fixed amount of data for 2 seconds or 5 seconds has been stored. So one hand you keep playing data, at other end data keeps coming and getting stored in the behavior. Now while studying congestion control, we have seen that TCP follows a sawtooth behavior. Sawtooth behavior basically means we are in congestion avoidance phase, and when we get all the X, we increase the bandwidth by 1, get all the X, again increase the bandwidth by 1. So my congestion window keeps increasing linearly. At some point in time when packet loss occurs, we set the congestion window to half, and then we start increasing it again. So it basically looks like sawtooth behavior like this. And that means it keeps increasing, then suddenly becomes half. That's also called AIMD behavior. Additive increase, multiplicative decrease. And because now the band congestion window keeps changing, That means server will never send data at the fixed rate. Based on the AMD behavior, it will keep sending at a different rate depending on what the bandwidth is available because of sawtooth behavior. If you get the hack, it will increase the bandwidth congestion window, and the moment congestion occurs, packet loss occurs, it drops the congestion window to half, decrease the transmission rate. So server would dynamically keep changing the transmission rate. It cannot never be fixed. Other thing is the major drawback with TCP is TCP guarantees you in order delivery. Let's say we are sending 100 frames and packet frame number 10 is lost. So even though receiver has received frame number 11, 12, 13, 14, the lying in TCP buffer, but till frame number 10 is delivered, frame 11 to 20 cannot be delivered to the application because TCP gives in order delivery. So till frame get transmitted, so because it doesn't get the X, server will retransmit frame 10, and if frame 10 again get lost, it will again time out retransmit. So even though client TCP has frame 11 onwards in the buffer, it cannot deliver because frame 10 is not there, and this retransmission could cause significant delay to the application. And primarily because of this reason, that retransmission could cause significant delay because packets are delivered in order. Initially, TCP wasn't employed for multimedia application delivery, and it wasn't very well encouraged. So we can look at the behavior of TCP send buffer and receive buffer. We have a video server, we have a client. Server would have the application buffer where it sends. Client has the application play buffer from where it reads, connected by a network. When another application sends, it goes to TCP send buffer. It will send data through the network. It will come to the TCP receive buffer at the TCP stack, and from TCP receive buffer, it will go to the client application buffer. Now, RT is the consumption rate, which is a fixed rate. So video has to be played at the fixed rate called RT. This XT is the rate at which server is sending. So this XT will keep on changing. Why? Because TCP follows sawtooth behavior. Depending on network bandwidth, this XT would never be constant. TCP congestion control constantly keeps probing the network bandwidth. If it's available, keep increasing. If it's not available, it decreases by half. So that means XT keeps on varying. So the rate at which this TCP receive buffer would full could be more than RT, could be less than RT, depending upon what the value of X is. And then we need to study what really happens when this transmission rate by server XT is less than R or less than or greater than R. R is the rate which is consumption rate. XT is the rate which is transmission rate by the server, and RT is the video application play rate, which is generally constant. We indicate time because X keeps varying based on the time. So does HTTP, so one protocol, the drawback was the retransmission could cause an issue, but UDP has two other drawbacks. One was repositioning required RTSP, another protocol. If using HTTP, you need to do repositioning, move ahead. HTTP has a support for called byte range. Let's say a whole movie is 10 megabytes, and currently we are playing at the byte number 1 megabyte, and suddenly user position moves ahead to position 5 megabyte position value. So rather than getting all the data from 1 megabyte to 5 megabyte, we can use HTTP request giving a byte range to give us the data from 5th megabyte onwards, next half a megabyte. Because we can HTTP supports byte range header, so if you do repositioning using byte range header, we can get the respective bytes rather than getting all the bytes, which wasn't the case with UDP, and that means HTTP does support user actions. And we don't need a separate RTSP server Next issue with UDP was the firewall does not allow UDP traffic. Firewall are configured to permit HTTP traffic because every user is a browsing. And since we are doing HTTP, so we don't have to put any special request for firewalls. But the major challenge still remains the congestion control because retransmission or network bandwidth could vary and you might have significant delay. Now, how this could be avoided, the network bandwidth variation, we can basically do two techniques called prefetching and buffering, and we'll study those with that techniques, buffering and prefetching, and then see how to do things basically work. It has been done experimentally, figure out that if user does not have to suffer any bad experience, and that means experiment is shown that if the network bandwidth or TCP throughput is at least twice the video consumption rate. So if my video consumption or play rate is 2 megabit per second, or that means the video encoding rate is 2 megabit per second. So as long as on the average, network gives me a bandwidth of 4 megabit per second, user would not see any bad experience and it will take care of that. So it works fine when network bandwidth is at least twice the video consumption rate. Then experiment has shown that one does see minimal starvation, there are no buffering delays. Even buffering delays, because buffer is there, data is getting more on the average, so buffer will get filled. Even the bandwidth falls to low values, buffer will become empty, become fall full, but user would not see a video frame or a video path. And that's the reason when YouTube started, before YouTube, the multimedia streaming used to happen using UDP. With YouTube, it started using HTTP because Bungie started improving a bit, and YouTube gave you a different encoding scheme. So you can choose whether you want 240, 400 KB this thing, or frame rate, or 600, or 780 pixel. Based on that, it can decide what the sending rate is. And because of TCP, you look at the network bandwidth, you will get a good experience. Quality might vary depending on the video encoding rate, but at least while playing it, you will not see a difference. Now we said that TCP handles the buffer playout using two techniques. One is called prefetching and other is called buffering. So what does prefetching mean? If I am playing at the rate of 2 megabit per second, that is my play rate for video. So if my bandwidth is more than 3 Mbps, that means client is getting data, a server is sending data at the rate higher than the video play rate. And that means whatever the extra data server gets, extra data client gets, it basically gets stored in the client buffer. And that basically means client is prefetching video because of higher bandwidth than the play rate bandwidth, and this prefetch video is stored in the buffer to be played later. And because of TCP streaming with congestion control, TCP always makes use of the best bandwidth available, so prefetching by default occurs with TCP. Primarily because of congestion avoidance phase, we keep probing the bandwidth, and based on the bandwidth available, keep sending data. So we can look at the example. Let's say my video play rate is 1 Mbps. Let's say network capacity is 1.5 Mbps, and that means the moment my capacity will bandwidth, the transmission speed increases 1.5, with the sawtooth behavior, it will fall down to 0.75, again increase to 0.75 to 1.5 Mbps, again fall down to 0.75 Mbps, and so on and so forth. So whenever fall down to 0.75 Mbps, it is actually less than the video play rate. But because of buffering, you already have buffered data, because average throughput is 1.5. So client is buffering at the rate of half Mbps extra, 500 Mbps extra. So with that rate, even though bandwidth falls to 0.75 with a sawtooth behavior, we still have enough buffer, and thus user does not see any video degradation and no freezing, something of that kind. So let's look at how does buffering work. We've seen this diagram. We'll do a little more analysis in terms of variations what typically happens. Now, assuming that my network bandwidth is higher, and at this point in time, this client buffer becomes full. When this client buffer becomes full, that means client won't read data from the TCP receive buffer. When it doesn't read data from TCP receive buffer, this receive buffer would also become full. When the receive buffer becomes full, we get a flow control into the picture. And by flow control, TCP receiver would say to the sender, my receive buffer is full, and this is called TCP zero window size. So this send buffer also full because it will not send the data. Even the application is sending, but receive buffer, sorry, sender buffer becomes full, and that means sender gets blocked. When sender sends send, there is no buffer available in sender buffer, so sender call gets blocked, and that means video application gets blocked, and we are wasting bandwidth resources or computing resources to the application at the server just because the buffer at the receiver has become full. Now this can become full either because user then a pause button. When user presses the pause button, no video is playing, but data keeps coming, so this buffer would get full. When a client application buffer becomes full and user is paused, that is not consuming it, so sooner or later TCP receive buffer becomes full. Because TCP receive buffer becomes full, it will TCP will say flow control zero window size. With zero window size, TCP sender will not send any more data because zero window size, but application is pumping it. So the send buffer becomes full, and when send buffer becomes full, when video sends, the application sends data, send would be blocked, and that means you're blocking a server application just because client has doesn't pass. Other is play rate is much smaller than the send rate, and sooner or later this buffer becomes full, and that's what would happen. So we can look at how does playout really happens, the video streaming part. So assume that the total client application buffer is B, and Q denotes the amount of playout buffer. That means this much buffer should be filled before we start the playout. Because we want to make sure that certain buffer is available. Because if we start playing out immediately when we get some data, we might see a freeze. So any multimedia applications, you always wait some time, some for basic buffer to full. So assume Q denotes the buffer size, which is required to play out the start the application, and B is the total buffer size. Obviously, Q is less than B because if Q is more than B, that means I've got the entire data. My buffer is not even there to play. I will never start playing. So Q has to be less than B, and we'll assume that R is the play rate and X is the rate, which is rate at which server sends. So look what happens. Data keeps filling up, data is consumed, and it fills up till the play point in time, and it server will keep playing, so it will consume data, application will keep sending data, so the data in the application buffer would keep on varying. And that is what is happening because this R is constant, this XT is varying. It may be more than R, it may be less than R. Sometimes it will become full, sometimes become less. But as long as it never becomes zero, a user would never see a problem that so much variation is there. Because user seeing a constant data from this is playing at the rate. So even though the buffer filling in the client application buffer keeps varying, user at the end, user experience is good because he does not see any pause and his experience is much better. Now we can basically say, compare the fill rate versus the play out rate. If X in general happens to be less than R, that means send rate by the server is less than the play rate. So even though you fill the buffer, because R is higher than the X, this buffer slowly will become empty. And when this becomes empty, there'll be video freeze. And because of video freeze, you will get a bad experience. And then again, you fill the buffer, you start playing it. So every so often, you would see a video freeze happening when X is less than R. When X is greater than R, client would never have a problem in playing because you're getting data more than the play rate. So some point in time, buffer will become completely full, and that means we are sending at the rate of X, client is playing at the rate of R, so buffer is filling on the average at the rate of X minus R, and after a certain time, at the size of B upon X minus R, at that time the entire buffer would get full. So how big the buffer we should make? If we keep too big a buffer, then that means we are trying to stay for longer, and if buffer is too big, we'll never have the issue of starvation because always would be data. But with too big a buffer, user has to wait that much longer before cloud becomes. So there's a compromise one has to make. How much you initially want to wait versus do you want to like to get wait in between your freezes based on the network conditions. So you always find a compromise to figure out how things happen. And how does controlling with prefetching and buffering, how does our user action work? Basically, let's say it does position forward. Because we have a byte range header, with byte range header, someone who done the assignment, using byte range, you can get a specific chunk of a file rather than the entire file. You can specify which part of the video file you want to get. You specify that, you get that file, and that especially useful when you jump. When you jump to a particular position, you can get the file content from that location onwards rather than the full file. And that way, HTTP provide inherent support to repositioning. And that is where it makes a difference, which UDP we couldn't support, and we don't need a separate RTSP server, and this is good part. The only negative part with position ahead is you already got data in the buffer. So let's say we are playing the video is 1 hour long, we're the minute 10, and we want to position to minute 20, and let's say our buffer data is for minute. So whatever data was there already in my application buffer from 10 minute to 11 minute, 1 minute, that is not being seen. So that becomes waste. You basically wasted the network bandwidth using the data, and we have to wait for a play out. So repositioning does end up wasting the bandwidth data, but that's the price you pay if you're trying to do HTTP. And that also means not only the wastage of bandwidth, server also consume resources sending the data from 10 to 11 minutes. That simply goes wasted, but user actions are unpredictable. So there's no way you can avoid this wastages, or you can minimize it. So you can find the optimal size. What should the buffer size be? Because larger the buffer size, more the wastage would be when you do buffering. So what are the main drawbacks of SSL? You can probably look at when client jumps to a future position. Let's say I was currently playing at the time T0. My application buffer is B, and that means I would have a data and I'm playing at the rate of R. When a buffer size is B, it will take time B by R to play. That means, so if client is moving currently from position T0 to any time between T0 plus less than T0 plus B by R, we would have a buffer in the application we can play. User would not see a freezing or bad application. But if a client moves to a location beyond T0 plus B by R, T0 is the location currently where it's being played, B by R because B is the buffer bandwidth, R is the play rate. That means B bar is the time required to play out the entire buffer. So if user moves ahead from T0 plus B by R, it is moving to a point where there is no data in the buffer. So data has to be fetched, and so it will take time. Then we freeze there, plus we end up wasting the bandwidth. Of course, by using byte range, we can get the required data, but there will be some kind of freezing that would occur. And whatever data we had, this entire buffer data becomes waste, and that is the basic drawback. As a human analogy, you can look at, you try to cook food, expecting people to eat, but people didn't come, or they say, we don't want to eat this food, you have to cook something else. So whatever you made simply goes as a waste. So the wastage occurs based on repositioning, and that's the drawback with HTTP. How could we handle with, can we avoid that, or can we minimize the waste? And that is where the improved version of HTTP called DAS, Dynamic Adaptive Streaming over HTTP, which came to address the shortcoming of HTTP. The major drawback is with video file, we stored on the HTTP server. When you get a URL, all the users get the same file. Different users have different bandwidth. Doesn't matter whether you have a phone, whether you have iPad or you have a desktop or laptop. If you got a single file, it doesn't really care what the user device is and try to play the same thing. So trying to play screen recorded at the high frame rate, playing on the phone with low bandwidth certainly would not give a good experience to the user. So if you want support from based on depending on the user device, depending on the bandwidth available, can we make a different quality videos and play those accordingly? And that is where the DAS comes in. So it takes care of device type, it takes care of client bandwidth, and basically support that where HTTP does not have any provision to do that. And because of that, the bandwidth varies. We simply get a very poor experience to the user. So what we do is we basically divide files into different chunks. And that is what DAS supports. So the way the DAS protocol works is it divides a given file into multiple chunks. If you look at Netflix, the whole movie, it divides into chunks of 4 second or 10 second each. And it gives you basically manifest file and gives you the details for each chunk. So if let's say my whole movie is 1 hour long, and let's say my each chunk is 10 seconds, that means I would have a 360 different chunks. Each of these 360 chunks would have their different URLs. Each of these 360 chunks are stored at different encoding rate. Some would be stored at pixel rate of 480 pixels, some would be 720 pixels, some would be HD rate, some would be high definition HD, some would be standard definition. So each of the 360 URLs would be stored and kept at different encoding rate. And each of them would have a different URL. So when client accesses a video, first what client gets is the manifest file, which provides all these URLs and encoding details of each of the URL. So what client does, client when it makes a connection, it measures what the current bandwidth is. And based on the bandwidth, it requires an appropriate chunk. When I start with, let's say my bandwidth is 1 Mbps, so I know that if for each 10 seconds, chunks are stored at the rate of transmission for 1 Mbps, 2 Mbps, 4 Mbps, 10 Mbps. So depending on the bandwidth, I'll request that chunk. And I keep measuring my bandwidth. Next time my bandwidth increases from 1 Mbps to 2 Mbps, so second chunk, I'll request not the same which was recorded at 1 Mbps, but at 2 Mbps. After the second chunk played out, I'm measuring my bandwidth, and let's say it becomes 6 Mbps. Then I'll get the third chunk, which is encoding at the rate of 6 Mbps and download. So what you'll normally see is it's continuous play out at the user end, and since that continuously played, and unless it is a very, very high action movie, minor variation in encoding rate 1 Mbps to 2 Mbps, as the user is engrossed with the movie content, it does not even see quality minor degradation, and user gets a good experience. And that is what this dynamic streaming protocol does. So user keeps on varying, measuring the user bandwidth. Based on the bandwidth, for each 10 second or 4 second duration, whatever chunk size is, it requires that particular chunk, plays that out, measure the bandwidth, get the next chunk as per the bandwidth. So the continuous play out, the minimum starvation, and if user does a fast forward, or user does a repositioning to the next other place, it knows with the next other place is which is the position in the movie. It has got all the chunk details in manifest file. It will request that particular chunk corresponding to new position. So let's say user at minute 10 in a 1 hour movie and it goes to position to 20 minutes, then it will make a request for chunk corresponding to chunk that starts at 20 minutes. It will get the 4-second chunk, plays out, get the next chunk and so on and so forth. It dynamically adjusts. So today, all video playing, whether Netflix, YouTube, they basically play using the dash mechanism. And that is how they basically dash work. Essentially, because of manifest file, intelligence is provided at the client side. Client knows when to request a chunk, what chunk to request. It makes sure that there should be no buffer starvation. If client sees the buffer is getting fast at the higher rate, it will request chunk with the low encoding so that it can get the data. If buffer is getting, so based on the current buffer size, based on the play rate, it can keep requesting appropriate chunk. Intelligent decides which video quality chunk should be retrieved based on the bandwidth. It retrieves that, and thus because of the different chunks, and you don't suddenly decrease from 4 Mbps to half Mbps. You know the network is decreasing, so decrease 4 Mbps to 2 to 1. And so because of the gradual quality change, user does not really perceive sudden quality change. There is no jerk, and user sees a continuous play and gets better experience. And when you get better bandwidth, it goes for higher quality. When you watch the Netflix movie or all these movies today, the client automatically dynamically adjusts based on the better bandwidth and gives you very smooth user experience. And that's why, because intelligence is moved to the client side at the end, not within the network, it gives a better experience. And that's the beauty or main characteristic of internet telephony, internet delivery, intelligence at the end stations. For a typical telecom network, we used to have a simple black phone. Black phone has no intelligence. Intelligence was in the network. When intelligence lies in the network, any upgrade, any change would be a very time-consuming process. When intelligence is at the client or server level, client can make any changes. Network doesn't require a change. So that means network doesn't have to undergo any change. And client development could be much easier. We can deploy a new client, make use of it, and it becomes better. And that is what basically Dash gives. So the movies today, Netflix, YouTube today, they move to Dash. But previously, YouTube started with HTTP streaming, but currently, some part may be depending on device, it may be still doing HTTP, but on the phone, it certainly uses the Dash. To summarize, we basically studied 3 kinds of applications: UDP-based streaming, HTTP streaming, and then Dash. UDP streaming has a main drawback that it is oblivious to network bandwidth. We need a separate RTSP server, firewall issues, HTTP addresses file, but because of retransmission, user may get a poor user experience. And then we get Dash, where my video file is divided into multiple chunks, and each chunk is encoded at different encoding rate, and based on the network bandwidth client buffer, client intelligently determines, making with the manifest file, which chunk to receive, and that gives the most smoothing experience to the user. So with that, we're done for today. And Monday we'll start looking at basically the CDN technology clustering and other part of voice communication, what typically would happen. Any questions, please feel free. Otherwise, thank you, we are done. Any question, let me know.